Well, hi again. We're almost done. This next chapter, chapter 13, is about states of matter. I'm going to go a little fast through it and try and minimize it. I had to give you some information so that you're ready for gases and gas laws. And that will have to be it for this year. So here we go. Living in Tuolumne County, we certainly know the smell of skunk, and you know that the skunk doesn't have to be near you for you to be able to smell it. You can usually smell it before you see it. And odors travel, and that's because gases and molecules are in motion and moving around and mixing. And that's what we're going to talk about. There's two types of energy. You might remember this from your junior high classes: kinetic energy and potential energy. Potential energy, the most common one we talk about, is gravitational potential energy. Raise something above the surface of the earth, it has potential energy that you've put into it by lifting it up. And then, of course, it falls, and in that falling, that is kinetic energy. So potential energy and kinetic energy in this situation, one goes up and the other goes down. You know that the right before it pounds the stake into the ground here, it's going to be moving the fastest. And once it gets to the ground, it has no potential energy at all. Okay, so it's an up and down kind of thing. There's also potential energy stored in chemical bonds, but we won't get to that this year. And you've probably all seen the Newton's cradle. You raise up the little dust toy, one of the spheres, and let it go, and that energy gets transferred, and out the other end. This is a silly cartoon, but I think it's pretty funny being in the position I'm in at any rate. So again, kinetic has to do with energy of motion. Kinema is the root word, Greek or Latin for motion. So cinema, like movie theaters, moving pictures. But we're going to talk about KMT, kinetic molecular theory, and it tells us, informs us a lot about how gases are going to behave, and that's because of their motion. Any object that's in motion has kinetic energy, and there are several tenets at several important points to this theory. The first thing, and this came from John Dalton's work, or he's the first one to put it out actually, all matter is made of little particles. And another little piece to that is that they're always in motion, unless, if they could, be at absolute zero. So here's our assumptions. According to kinetic molecular theory, we assume that gases are teeny tiny, which they are, little spheres like BBs, and have insignificant, essentially zero volume. They're moving all the time, rapidly, really fast, in unplanned motion, but it's a straight line motion. Okay, so just zip, 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 zip all around. Okay. They have what we call in physics perfectly elastic collisions. That means they retain all their energy when they bounce off of the wall of a container or each other. They don't slow down. And then the other thing that is part of this theory is that there's no forces acting to make the particles want to coalesce, form bonds, form liquids and solids. Most of the time, this is really perfectly fine to think this way. It's not a problem. So this little picture is supposed to show the little gas molecules hitting the walls of the container, of a clear container, smacking into it, and then bouncing straight off again. Another thing you'll see a lot in these kind of diagrams is little streaks or tails behind the particles. Oh, behind the particles, yeah. That's how we assume. And the longer those tails are, usually the faster they're supposed to be moving. For example, this one would be moving faster, this one would be moving slower. Every time a particle hits the side of a container, it exerts a force, but they're traveling in straight lines. No 180s or 360s. They're just going in straight line paths. And I guess that is a 180, huh? And this force that's being exerted on the container, force over area, is pressure. Super important when we talk about gases, pressure. There's two main conditions where this totally falls apart, this theory. And that's if the temperature is very low. That means the particles are going to, I mean, like really, really, really low, lower than you would go out and make a snowman in. That causes the particles to be to slow down and coalesce together. Also, if you exert tremendous pressure, like this is a pressure cooker. Some of you might have an Instapot. That's the newer version of a old-fashioned pressure cooker like this. You have it sealed, clamped down, and the pressure can build inside, and that forces the particles together. All right, so gas pressure. One of the things that we know with kinetic molecular theory is if they're always moving, that means they're going to be colliding with the container, exerting pressure, like I said. So gas pressure is a force over an area. Empty space pretty much is what we call a vacuum, not a Hoover or a Dyson or a Roomba, but it's lacking all matter. There's matter out here, just not very many particles per cubic meter. Atmospheric pressure is what results from all those particles bouncing and hitting you and hitting the earth and hitting each other. All those simultaneous collisions of all the billions of particles is what creates pressure. So how do we measure pressure? The first person to come up with a workable barometer was an Italian physicist, Evangelista Torricelli, and he actually was Galileo's secretary, I think, for a while towards the end of his life, Galileo's life. But Torricelli was, there it is, the inventor of the barometer. At the mid-1640s, he developed a system to measure atmospheric pressure. This is an old style barometer, and in the video you'll see they'll talk about mercury being used. Torricelli originally used water. That's what everybody used at the time. Very inconvenient. Normal atmospheric pressure can cause a column of water to be 30 feet high. Not very easy to work with. So 10 meters, 30 feet. So he came up with using a dish of liquid mercury, and this video will explain the history and how it actually works. Barometers, this is one thing that most people don't, they have to think about. Liquids don't compress. They push out of the way, but they don't compress. Gases are compressible, liquids aren't. So when atmospheric pressure, when the gases in the atmosphere are banging on the surface of the mercury, it will displace the mercury, and if it's a container like this, it has nowhere to go, but it will go up the tube. And so that movement of the mercury liquid up the tube under high pressure, and then of course if there's less pressure on this outside surface, then the mercury can fall down. So this is showing sea level, about 760 millimeters of mercury. That's normal atmospheric pressure. Up at the top of Mount Everest, 253, about a third, which means you're going to need to wear probably a mask and get some oxygen. This is an old style ship barometer. It uses just liquid water. It just has food coloring in it, and it's sealed all the way around. But this little tube here, little spout, is open to the atmosphere, and the water, the air can push on this and push down if it's high pressure, or it'll go up the tube when it's low pressure. This is the style of barometer that we have in the classroom in the middle room right by our door. You might have noticed that wooden cabinet when you're going in to get Chromebooks. This is not ours. I don't have a lock on ours, but it's just the same style, and the dish of mercury is down at the bottom. There are also fluidless barometers, and so some of you may have seen these before. Maybe your grandparents have a barometer like this. They're called aneroid, and then this is actually a altimeter. This is using atmospheric pressure to guesstimate how high up you are. And small planes, that's what they have for their instruments. How does it work? There's a little cushion inside, a little lever. As the atmospheric pressure increases, the cushion gets squished, causes the dial to go higher. As the atmospheric pressure drops, the cushion can expand and the dial goes lower. The unit of pressure is the Pascal. That's in the SI unit, but we're going to use kilopascals because pascals are so small. Also, you might remember when we first talked about molar volume, 1 mole of any gas at STP. So standard pressure is 1 atmosphere of pressure. That corresponds to 760 millimeters of mercury. Okay. There's also units called torr. Sometimes weather people use millibars. You might see it as inches of mercury. You will also probably be familiar with PSI, pounds per square inch. So when you inflate your tires on your car, most passenger cars have tires that need pressure about 30 to 35 psi, so roughly double 2 atmospheres worth of pressure, if you will. 14.7 pounds per square inch. Every square inch of your body is getting bombarded with almost 15 pounds of pressure. But these are all interchangeable. And this number is actually 101.325 kilopascals. I won't play this for you guys, and I'm not going to ask you to watch it, but it's in the list if you are interested. So one of the things you have to be able to do is convert kilopascals, convert from millimeters of mercury into kilopascals and atmospheres, and that is outlined in your textbook in this section. All right, so kinetic energy and temperature. This is a really important concept. You need to understand that if your temperature goes up, the kinetic energy of the particles goes up. And so here's this diagramming that I said before. Little short tails moving slow, long tails once they're heated up. Low temperature, high temperature. Temperature is a measure of the average kinetic energy of all the particles. Every time a particle strikes the thermometer bulb, it transfers energy. Think about that little Newton's cradle thing. It transfers energy to the liquid that's in the thermometer. Then the liquid will expand. Things that are warm typically expand, and that's how thermometers work. So when you look at a sample, they're not all at the same exact kinetic energy. Okay, it's an average. Some are going to be moving slower, some are going to be moving faster, and most of the particles are going to be in the mid-range. So here's a graph that represents average kinetic energy. So very few are going to be essentially not moving. Kinetic energy is 0. Then a bulk of them are going to be up in this range. Okay. Some of them will be going really, really fast. But for a cool sample, most of them are going to fall under this curve. As you warm up a sample, there's still going to be some that are going really slow. Okay, the curve kind of spreads out a little bit. More of them are going faster. So the area under this curve shifts as the temperature goes up. This is the diagram from your textbook. Again, a little different shape than that last one. Most of the things that are going slow, when you have a low temperature, are going to be under this area. When you have a higher temperature, it's going to be shifted. But there could be some going really, really fast still, even in the cold stuff. All right. The guy that came up with the temperature scale, the Kelvin temperature scale we have to use with gases, was William Thomson. He was Lord Kelvin. They gave them extra title names. He did a lot of work with energy. He's responsible for kind of coming up, it says finalizing the laws of thermodynamics. He is credited with the absolute zero scale or the Kelvin scale. He also was in charge of getting that first transatlantic telegraph cable put at the bottom of the Atlantic Ocean. And he has 21 honorary doctorates on top of the one he earned himself. Pretty crazy. So, silly, silly, silly. He was also kind of a rude son of a gun and didn't like women, but, you know, what are you going to do? All right, so, Fahrenheit temperature scale, Celsius temperature scale, Kelvin temperature scale. The numbers change, and the only thing that changes on the Kelvin scale is you add 273 to the Celsius temperatures. So freezing point of water is 0 Celsius. It's 273 Kelvin. There are no negative numbers on the Kelvin temperature scale. It goes from 0, absolute 0, to 373. And you don't use degrees with kelvins. You should use a degree symbol with Celsius and Fahrenheit. This is a gizmo that I actually have in the classroom. I may be able to videotape it. It's a stainless steel sphere with a fixed volume. It won't expand and contract like a balloon. This part right here is where you could put a bike pump to it and get it to read a certain pressure. And then that's just as a handle to hold it. When I do this demonstration, I put it into an alcohol and ice water bath, an ice water bath, a room temperature water bath, and a boiling hot water bath. Probably what you might understand is that the pressure is going to go up, right? Those particles are going to go whoa, 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 go crazy. The higher the temperature, the faster they move. That's kinetic energy, right? So people had looked at this before and realized, hey, you know, that looks like a linear relationship. Look at all those data points. And even with just 4 data points, I usually come up with pretty good results. You know, it can get less than colder than the freezing point of water. People did back in the late 1800s as well. And when you see a straight line, of course, you know that the formula of a straight line, y equals mx plus b, b being where it crosses the y-intercept. You can also figure out where it crosses the x-axis. And what Kelvin did is extrapolated. Okay, so you notice the line is dashed because we didn't actually collect data in this range. We extrapolate back, 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 back. When is, this is pressure on this axis, it's not on there, sorry. When is pressure going to be 0? When does all motion stop? When are they not moving? Minus 273 Kelvin, minus 273 Celsius, which is 0 degrees. 0 Kelvin, I kept saying degrees, sorry. This gentleman uses equipment I don't have, but it's kind of similar, so you can kind of see the metal sphere here, and what we would do is put it into these large beakers. This is with equipment that from Pasco that I don't have. All right, so last little bit, Kelvin temperature is directly proportional to the average kinetic energy. The higher the Kelvin temperature, the faster they're moving, the higher the kinetic energy. And again, it's an average. And then finally, this is just a picture. You can't really tell what it is, but this is a picture of a device that they've used to cool down sodium vapor to nearly absolute 0. They've come within a few thousandths of a degree. It's really amazing. And that is it for today. Hope you're well. Take care.